Hello, everybody. Welcome back. I'm broadcasting again from home today, but I remembered the good camera so you can see me in HD. Okay, so today we're doing chapter 6. This is the first half, and we're going to be talking about the normal distribution, also known as the bell curve. So I put a little bell. Okay, that's slide 1. Slide 2. So we're going to talk a little bit about what it is, the history, and why we care. We'll talk about the properties of the standard normal distribution. And then in part B, which will be the next video, we'll talk about calculating z-scores and interpreting z-scores. Okay. So the normal distribution, this is slide 3. The normal distribution is unimodal, it's symmetrical, and it has a bell shape. Pretty straightforward, right? Why do we care about it? Now, many dependent variables are assumed to be normally distributed, for example, math ability. And we can use statistical techniques to make inferences about the values of variables that are normally distributed. For example, it allows us to predict the frequency of times that a score will fall into a particular range. So whenever you hear a statistic that has something about the error within 3 points of such and such, then we're using properties from the normal distribution. Most basic statistical procedures assume that the values of variables are normally distributed, and almost all of the statistical techniques we're going to learn this term make that assumption. There's just one that doesn't, and that's going to be way at the end of the semester. Okay, so an error-filled history. I'm on slide 5, and if you would do me a favor in your copy, change that title, add an N, and it should say an error-filled history. Okay, so Abraham de Moivre was an 18th century statistician and a consultant to gamblers. If you look at the history of statistics, you find that gambling and statistics kind of go hand in hand, which is kind of funny. He noticed that if you flip coins over and over and you graph how many times you get heads, an interesting pattern emerges. And so that's what that graph is underneath his picture. And it kind of looks unimodal, symmetrical, and sort of like a bell. Now, astronomers Laplace and Gauss saw a similar pattern if they graphed errors in their measurements of stars and such. So we usually think of astronomy as just being very precise, but actually the instruments that were used in the early days of astronomy were very imprecise, and you could mathematically figure out where a star should be and then measure it, and your measurement may or may not correspond to what you figured out mathematically. So they could graph where the errors were, or so most of the times the errors in their instruments were pretty close to where the stars should be, but every now and then they would get a really wacky measurement with their instruments. Okay, so then later Quetelet and Galton implied the idea of normal error to measurements of people, which unfortunately led to the horrible and horrifying eugenics movement. So Galton measures, I think it was chest circumference of, a whole bunch of people and men, and he decides that, well, whatever the average is must be what, was intended to be right, okay? So anyone who was off the average was abnormal. Their chest measurement had a lot of error because it was off the average. So basically, they were taking this idea of the average and giving it way more importance than it should have been given, and applying it to the idea of people. And of course, we know that diversity is normal and natural, but to them, anyone who deviated from this average, and again, it was physical measurements at first, was considered deviant, how we use it now. And then the eugenics movement was about eliminating those people who deviated from what these individuals considered to be normal. Okay, so slide 6. But we're not going to make that mistake, right? We're not going to believe that the average is the only way that things can be. Okay, so the normal distribution, the parameters mu for the mean and sigma for the standard deviation define the center and the spread, right? We remember mu and sigma from last time. And that's slide 6. The thing is that you could have any number of different normal distributions, right? Because we're just saying unimodal, symmetric, right? And basically bell-shaped. So there are all these different normal distributions. So how can we really use them to make any kind of statistical inferences? And what you see here is, for example, the green one, the kind of flattish one, it has a mean of -2 and a standard deviation of 2. Whereas the blue one all the way over to the right has a mean of 2 and a standard deviation of 1. So, and of course, there could be any kinds of distributions that you can think of. And so the solution was to come up with a standard normal distribution. That's slide 8. Now, slide 9. Here's an example. Imagine an IQ test, okay? An IQ test typically has a mean of 100 and a standard deviation of 15 and a normal distribution. So, mound-shaped, symmetrical, unimodal. We know that 68% of people will score within 15 points above or below 100. So 68% of people, if the distribution is normal, will fall within +1 standard deviation or -1 standard deviation. Now, if you go out to 2 standard deviations, about 96% of all people will fall within 2 standard deviations, which is within 30 points of 100. Okay, next slide, slide 10. And so basically this is a trick that we know about standard deviation. As long as the distribution is symmetric and unimodal and that mound shape, then we know that there's about 34% of people falling from the mean to 1 standard deviation. Then another 16% from another 13.6% from 1 standard deviation to 2 standard deviations, another 2.1% out to 3 standard deviations, and so on, with only a few people left in those tails, extreme tails. Okay. The reason we know these percentages is because we can transform the values to a standard normal distribution, so we can standardize them. That's how we know these things. This is slide 11. Okay, so 68% plus or minus 1 standard deviation, 95% plus or minus 2 standard deviations, and 99.7% of observations plus or minus 3 standard deviations. Slide 12. So basically, we're used to standardizing values in our head. So for example, you know that 90 out of 100, a score of 90 out of 100, is basically the same as a score of 45 out of 50, which is basically the same as a score of 9 out of 10. It's 90%. All A's, 90%. okay? But we can convert them to percent to put them all on the same scale. Now, transforming a set of values to the standard normal distribution is called standardizing them, and puts them on the common scale of standard deviation units. Okay, the unit is standard deviations. We used to, the unit was inches when we measured height. Here, the unit is going to be standard deviations. Standardizing, this is slide 13. Standardizing, we're transforming our non-standard normal distribution, so all those various bells that we could graph, we're transforming it into one where the mean is 0 and the standard deviation is 1. Okay, we're transforming it. The mean is going to be 0, the standard deviation is 1 in this transformed world. So the standard normal distribution, mean is 0, this is slide 14. Standard deviation is 1, and we're going to call these new values, these standardized values, z-scores. The area under the curve is 1, which makes it easy to calculate percentages. Okay? So remember those M&Ms when I said, hey, remember this because we're going to be able to use this to calculate percentages? Well, if 1 pi, and then we took that one circle pi, and if we make it into one mound, then we can figure out the percentages within that. Okay. Which is kind of a cool little trick. And it all came from flipping coins. Okay. Next slide, slide 15. So basically, when we calculate a z-score, we're solving a formula to indicate how many standard deviations away from the mean a particular score is. So we're finding the distance between a mean and a score and determining how many standard deviations that is. Slide 16. So here's how you calculate z. Whatever your value is, minus mu, or the mean of the population, divided by sigma. Okay? That converts it to standard deviation units. And you know that sigma is for standard deviation. And so the z-score is the number of standard deviations above, if it's positive, or below the mean, if it's negative. Oops. Oh, and that's the end of this presentation. I was like, where's the next slide? So that's that. And this is to be continued because in the next video we'll do some actual examples, which will kind of make this make more sense. Okay, see you soon.